So yeah, we're going to pick up where the last lecture's left off, but go into a little bit more detail. So you've been given some conceptual understanding of what UQ is. This is a statistics lecture, so it is going to be focused on that probabilistic view that Amy was describing, and specifically building on this notion of intervals, specifically confidence intervals, that Mikhail was describing in the first part. So the first part, you've been told what a confidence interval is, okay, but we actually need to estimate it, right? So, okay, we have, you've been told its definition, but the definition isn't enough. We actually have to then estimate that confidence interval itself. So it is something that we estimate, it's not usually given to us. So how might we do that? Well, one common technique which I'll cover is called the bootstrap, which is quite a universal technique, but I think everyone should know about if you've not covered it. Who's covered the bootstrap before in the class? And who has not? Okay, that's a great mix. That's great. And then the other one is the CLT. That's not a type of sandwich, for those who have learned already. CLT, it's CLT, it's central limit theorem. Who's covered that in the statistics class? Yeah, and who hasn't? Okay, so that one will covered, right? And I say and or because these ideas of bootstrap and CLT actually kind of overlap a little bit. Sometimes we might use combinations of them. So that's going to be the first one. Second part, we're going to jump topics, if you'll permit me, and go into time series and spectral analysis. A lot of you in your talks yesterday were describing time series and spatial statistics problems, so I think it's great that today I can talk a bit about time series, and tomorrow Mikhail will go into spatial and spatio-temporal combination of space and time, and I think that will hopefully be very useful for your research. Part one is just going to be kind of independent data, so if we observe something many times, how can we measure our uncertainty? But of course, in reality, we're dealing with dependent data, not independent data, in the form of time series, spatial data, or otherwise. And that's what part two will build towards. And then part three is a bonus section, and I'm going to keep you all in suspense on what that is. You may have some ideas already. Let's see if you can guess what it is if the lecture goes on. I like to leave a bit of suspense on top of the structure imposed. So, part one, we're going to try and estimate uncertainty, specifically confidence intervals, using the bootstrap and or the CLR. So, what is the bootstrap? Sorry for the change of color, just to wake you up. What is the bootstrap? Well, let's suppose we have a population of things we want to estimate. Think of it as the ocean, if you like, our ocean, and we take a sample from that ocean. So maybe you can almost think of it as putting a bucket in, right? And that is the data, right? And in this case, just for illustration, we've got white balls and red balls. But we sample this bucket, but we don't know the colours of the others. It could be white or red, and I suppose it could be a different colour. And we can extend this principle to continuous data as well, right? But we sample a finite amount of continuous, categorical, or discrete data in this way. In this case, it's categorical, white or red. And now that sample, if we've sampled well, maybe we haven't data. We see that it's a spatial we sampled all from the same region. But let's assume we've sampled well across our population. Then our sample is representative of the population. And we might say, okay, our estimate is that 3/7 of the balls are red and 4/7 are white, right? But we want to put some uncertainty on that, right? We want to communicate some uncertainty with that. Because yes, we know for sure 3/7 of the balls in the sample. Okay? That we know with certainty. Right? But we don't know for certain if the population is 3/7. Right? So there's a leap that we make there, and that's the key part in communicating the uncertainty. Now, in an ideal world, how could we reduce the uncertainty on our population estimate, well, we would try and probably increase our sample size. If we sample from all of the population, then our uncertainty would go to zero. So we have to complete them out. But rarely can we do that. Sampling is expensive, right? So let's say we've sampled as far the ocean ship has gone, and that literally or metaphorically, that ship has now sailed, we can't collect any more data, right? So ideally we get a bigger sample, but we can't. We're stuck with what we have. This is our sample. We're stuck with what we have, and yet we need to try and communicate our uncertainty from. The idea of the bootstrap is to say, fine, we don't have anything more than the sample of the things that we've been given, but let's resample from that sample. And the idea is that we can resample many times. Now you'll notice that our resamples are still size 7, but they have different numbers of red balls each time. And what we've done is we've resampled with replacement to keep that. Think there's a bag with balls in, you pick a ball out, you notice colour, you put it back in, shuffle the balls again, you do it again. And the key reason to do that with replacement is that allows us to do it 7 times, but then to do it again 7 times, to do it again 7 times, and each time get a different answer. Right? Because if we did it without replacement, we just get the same answer every time. Right? We just pick all the balls out and we get 3 reds every time, and we'd get 0 uncertainty. That's not what we want. We want some perturbation of what we've observed. And we just do this as many times as we want. Okay, and this time we're saying, well, 2/7 of the balls are red, 4/7 are red, 5/7 are red. It's changing each time, you see. And if we keep doing that, we get a distribution. Right? So there are 3 distributions in those dots. But if we now consider, well, we can get anything from 0 all the way to potentially 7 red balls, and I think that one didn't happen, but we had 0, 1, 2, 3, 4, 5, 6 happening a different number of times, and you can see now we have some kind of distribution of our centered around, somewhere near around our 3/7 estimate. And we can calculate uncertainties. Okay. So in a nutshell, that is as simple as that. For those of you who didn't know what the bootstrap is, no equations needed. In one slide, we can explain what the bootstrap is. Right? Now, some of you may think, no, I don't know about that. I'm not sure I believe you that actually works. Right? Let me show you in code. Okay, so for those of you who want to run the code on your own laptop, I apologize, it's in MATLAB. I am a dinosaur, and I don't know how to program in Python. But if you are not a dinosaur, you would know how to download the code and convert it into Python before I even speak my next sentence. So feel free to do that. But the other reason I give this link is afterwards. If you want to read my code, go to my GitHub page in OceanUQ, and you can see the code I'm about to give you. You can convert it into your language of choice afterwards. But I thought I'd show you this in code so that we go, you don't just get death by PowerPoint this week. Now you're going to get death by MATLAB. Let's see how we get on. So I'm going to show you in code. Okay. So is that big enough? Back? Yeah. So yeah, welcome to my bootstrap demo. So I'm going to generate you some toy data from a t-distribution with me 0.5. I actually picked this 0.5 and I'm motivated by Wendy's talk, who asked us yesterday, can we confidently say SST has increased by 0.5 since 1950? Yeah. So let's generate some toy data. I picked a student t-distribution, for those of you who don't know, because it's heavy code. So I'm going to run this code and I'm going to have a sample size of 100. So I'm going to draw 100 values from a t-distribution. It's got what's called 5 degrees of freedom, which is quite heavy-tailed. It's not that Gaussian. And I generate it here, and I'm just going to plot you a history of those values. Okay? So there's a histogram of those values. Should be big enough for you. And overlay is the student t, probability density function, and the normal, right? And what you can see, the key thing, difference between those is the tails, right? So these values of -5, +5 would not have happened with a normal distribution, very unlikely, but with a student t they do. So I do always sort of encourage you to test, if you're running a simulation environment, think about throwing like a t distribution, something with some outliers, and really test your methods that you use, as well as your actual methods for inputs, to see if they're working well. And that's sort of the main difference between those, so I've overlaid those. Okay, so that's the data. So these are 100 estimates. Think of these as 100 estimates of how much SST has changed since 1950 at 100 different independent locations. I've given you a pretty wide range because I'm making the problem difficult. So now it's not realistic, in some areas it's gone up by +5, and others by -5. But the question was, this was a mean of 0.5, so I've shifted the t, and we have a distribution around 0.5. So we might want to test Wendy's hypothesis of does this data support a 0.5 increase in SST, or any increase? Or actually, would we say it could be negative or positive in this data? Right? So the obvious thing that you see here that I've got in the code is the mean of my sample. So this mean here, down here, is the mean of those 100 values is 0.59. Right? So it's actually higher than 0.5. So we might just stop there and say, across 100 locations, SST has gone up by 0.59 degrees Celsius, full stop. But as the message has said, that is not acceptable in science, just to say it's gone up by 0.59. We've got quite a wide range of values. We want to communicate that uncertainty. Right? So let's close that part. Moving on to the next part. In an ideal scenario, make it a bit bigger. In an ideal scenario, we know the true standard deviation of the data. So this is a problem, actually. In reality, we don't. And when we know the true standard deviation of data, if we're trying to report uncertainty on a mean, that's quite easy, actually, because from theory, in line 17, the standard error, the mean, is the standard deviation divided by the square root of our sample size. You've seen that formula before? Yeah, so some of you have, some of you haven't. And the point is that we have a standard deviation of our data, which in this case we know what it is, if we were sort of Oracle, and we divide it by the square root of our sample size, and we have a standard error for mean. Okay, so in theory, the standard deviation, this bit here, is the square root of degrees of freedom divided by the degrees of freedom minus 2. That's just a formula for these. It's a little bit more than 1. And then we divide it by the square root of n is 100, so by 10. So if we run that, we get a standard error from the theory of 0.129. Okay, so this is a measure of uncertainty. It is, because it's a standard error. An error is the difference between an observation and the proof. Standard error of the mean is measuring the standard deviation. So it's what we either get from theory or from a large number of observations. It's a collective measure of that uncertainty. So we're doing better now if we say the rise in temperature is 0.59 plus minus 0.1291. That's a start, right? But this is an ideal scenario. We don't know the true standard deviation of the data, right? We don't usually know that. So now building on one thing that Amy talked about yesterday, second ideal scenario is that we repeat experiments. We do Monte Carlo experiments. So I've just shown you 100 t-distributed values. Well, we could repeat that 1,000 times. So 1,000 times, I'm going to repeat that experiment. So the ship goes back 1,000 times. So it's a very ideal scenario, right? That's not going to happen in practice. So the ship goes back 1,000 times. But let's just say that we don't know the theory, but we can repeat the experiment to death. And in an idealized setting, that is a bit like knowing the theory. Okay, so if we repeat that, And we generate loads and loads of data. So that's all our Monte Carlo repeats. And then we compute the mean along each of those trials, and each of those Monte Carlo repeats. Then we can approximate the standard error via Monte Carlo by taking the standard deviation of those means, okay, in this line. Now, if I plot that, what we get, these are no longer the distribution of estimates, these are the distributions of our estimates of the mean across our Monte Carlo sample. Right, so they now become concentrated. They've shrunk in around the truth, the unknown truth, 0.5. And I've overlaid a Gaussian distribution over that. And this time it's a much better fit. Okay? And why is that a better fit? Yeah. Sorry?
It's the means.
Yeah, and so it's Gaussian because of
Central limit.
Central limit theorem. Yeah, thank you. So what you're seeing here is the central limit theorem. Now, this works for any original distribution as long as it has finite moments, finite mean and a finite variance. That under the assumption that you're averaging a bunch of independent realizations from that distribution, the mean will be distributed like the Gaussian. Okay, so that's just a quick crash course on what the central limit theorem does. And when we can use it, like Amy said, we would like a distribution of our answers. So in an idealized setting, I've given it to you there. But we're still in an idealized world, right? Because I've repeated the experiment. But we can't always do that. With a model, we can, but with real data, we can't. So how do we do it with real data? So, okay, let's close that plot. We only have x, right? Well, I generated y, which is a big number of repeats, but we started with just x, a length 100. So this time, rather than doing a Monte Carlo repeat generating new data, I resample from that x. Look how few lines of code it is. In MATLAB, it's just data sample. I just sample from x with replacement, and I'm going to do it 1,000 times again, generating length 100, just like we saw in the first slide. 1,000 times, I'm going to resample those 100 points with replacement. Right? And in principle, we can make this number as big as we want, but at some point, there's no point. The benefits will go away because you're not adding new data, right? Remember, you're not adding new data. You're getting the same data over and over. You're trying to estimate the uncertainty. You do that. This time, you take the standard deviation of the means across our bootstrap, for example, right? So, before we have a theory of standard error of 0.1291, the Monte Carlo almost bang on the theory. So we take the standard deviation, standard error of our mean estimates, we get 0.1285, almost exactly the same. But these were both cheating, right? We wouldn't have these available to us in practice. It's what we'd like to report, but we can't. This is what we can only report if we can repeat experiments. What do we get with the bootstrap? Let's run it. From off. Standard error with the bootstrap, 0.1330. Now, it's really remarkably reasonably close, okay? More on that in a moment. And I spoke to Shen about it and drive back yesterday, and he's like, oh, you're going to cover the bootstrap? Yeah, it works like magic, right? And there is kind of a magic about the bootstrap. It's like, it almost gets you scratching your head, why does this work so well? Just to resample from the same data set, rather than repeating the same experiment. And in many, this is why I'm plugging the bootstrap today, because some, I don't know where Mikhail ranks this, would say since in the last 80 years, this is in the top few, maybe the number one statistical development in terms of methodology or statistical discovery in the last 80 years. Would you agree with that?
Yeah, in the top. I maybe not number one, but I would put it in like, let's say, top 10.
Top 10. It makes Mikhail's top 10. It makes my top 5. Yeah, go
on. So it looks really great how close you can get with this bootstrap of the sampling method. Does that precision of that error decrease if, like, let's say your sample's only like 10?
Exactly. Yeah, great question. Yeah. So this is not a silver bullet. Now I'm giving balance to my huge plug. Top 5, yay, but doesn't mean that there aren't issues. So yeah, you've already identified one. So let's see. So let's look at this in more detail. So I'm giving you one number. And we should study this a bit more. So before I do that, how about the actual confidence intervals? So I'm giving you these plus minuses, but Mikhail told us about 95% confidence intervals. Well, there's a few ways you can do that here, which is why I mentioned you could combine CLT and bootstrap. If we plot a figure of our bootstrap estimates of the mean, yet again, they look pretty Gaussian. There's a central limit theorem that takes that. So again, we could fit a Gaussian, and we can create our confidence intervals from that Gaussian. This block that Mikhail helpfully kept on yesterday. This block here exactly from that block. Get our confidence intervals. That's one approach. But the smaller sample sizes, or for statistics that point estimates that are a bit more awkward than the mean, sometimes we're not estimating the mean, we're estimating the variance, or we're estimating the lucidity, or we're estimating, I don't know, other oceanographic point estimates out there. This will not always be so Gaussian, right? So that's why, okay, Gaussian works here, I'm working with the central limit theorem, doesn't always kick in so quickly or so nicely. So actually, the common approach is not to fit a Gaussian here, but to do what's in line 53 and 64, which is order the data and take percentiles. So we've got a bunch of bootstrap estimates, we can order them, take 2.5, 97.5 percentile, and we can get a bootstrap confidence interval. So now, finally, I can report my confidence interval for my 100 SSD observations from a D distribution. And I'm saying 95% confidence interval spans 0.34 to 0.85. And we've moved over, like Vanessa said at the beginning, we want one number, now we're going to two numbers. So we're improving, right? But we could also take the whole empirical distribution if we think our bootstrap is performing well. So we're starting to get distributions, intervals of uncertainty. Okay? But moving on. Okay, but did we get lucky? I just showed you X, right? But was X a lucky draw from that T distribution? Did I fix the seed and conjure, right? Let's try running on all those repeat samples we did in our Monte Carlo experiment. So now we've got that Y. So for each of those Y's, we do a bootstrap estimate of standard error for each of them individually. So let's see how our run performs. So I can't be accused of cherry picking. Now if we do that, we see a thought-provoking graph, in my opinion. Because I think before we were pretty close to the truth. But this is our kind of true standard error that we'd like to report of 0.125, whatever it was earlier. Yeah, 0.129, sorry, this red line from the theory. Now, if we bootstrap across all of those, you'll see the bootstrap isn't always going to hit exactly where you want it to. It's spanning anywhere from just below 0.1 to above 0.2. So this is one take-home message for all of you at home, is that when we do point estimation, yes, our points are estimates. Now, when we do confidence interval estimation, our confidence intervals are also estimates. Our measures of uncertainty are also inherently estimates. They have their own uncertainty. So now we are thinking of the next level of uncertainty. Right? There is uncertainty in our uncertainty. And that is what this plot shows you. Sometimes you will underreport the uncertainty, and sometimes you will overreport the uncertainty when you're doing data-driven uncertainty estimation, right? Pleased to see the philosopher nodding at the back. You're okay with me going to higher level uncertainty? Yeah. So this is this is another, like, Amy challenged you, like, demand uncertainty from the community. Now, I don't think the world is quite ready for uncertainty of uncertainty. Much, but you guys should be conscious of it, right? So whenever you see an uncertainty estimate, know that it is an estimate of uncertainty. You could be underreporting or overreporting the true uncertainty, and that's what this figure represents. Here I've used the bootstrap. I can use any method: central limit theorem, Bayesian statistics for credible intervals, whatever. Those uncertainties that you get might be under or overestimated. And that's just one take-home message I wanted to give you. But in defense of the bootstrap, it's reasonably well centered here, despite this being a heavy tail T distribution. It's doing decently, it's hitting the right ballpark. Okay, you asked about sample size. Let's run it. So, let's put a stop there, yeah. And first I'm going to increase it to 500. So we're going to see what happens if we have more data. If that shape didn't go back to that 500 points. What we start seeing is a better so now the theoretical standard error drops because we have our uncertainty is decreased from our bigger sample size and the quality of our bootstrap estimated down pretty to the 3, so it's just below 0.06, and we're always getting between 0.05 and 0.07. So in this case, we're doing pretty well with a big sample size. So there's a kind of convergence happening here. We don't need to go into the theory. Let's make it 20. Why not? This is like, stress testing my code. Right? 20 observations with SSD or whatever we say here. Now, it's actually not horrendous. And this is why the bootstrap is also popular, but with caveats for small sample sizes. It's roughly in the right place. We've only got 20 observations. We expect this to break down. We might get half the uncertainty, we might get double. It's pretty bad, but often we might be in the right area. So it's not horrendous, but sample size is a factor. But there's a bigger issue. And can someone guess what a bigger issue would be with applying the basic bootstrap? So the bigger issue is, okay, what if the data is correlated? And it's exactly what Amy talked about yesterday. Spot problem. What if our data in some ways is correlation? That can really mess things up. So what I've done here is just correlated neighboring points in a time series. So in a vector of points, so neighboring points have a correlation of 0.3 and a correlation of 0 otherwise. So points 2 or more apart are uncorrelated, but neighboring points have a correlation of 0.3. So I've added just a little bit of correlation, right? And I'm going to generate lots of data. I'm going to show you how well the bootstrap performs versus the theory. Now, if we run this, we do really bad, right? So now we want to be estimating this. We are consistently underreporting the uncertainty if we ignore the correlation data, right? Why is that happening? Well, one way to think about it is if we have positively correlated data, it's a bit like having less data, right? Our effective sample size is smaller. But we pretended we've got independent data, so we're overconfident in our uncertainty estimation. Actually, we should be further out. So that's the second take-home message for you. Beware. Okay. So that concludes part 1. Just to sum up, bootstrap. There are some really nice advantages. Very simple method. Understand, communicate, implement for calculating uncertainty. Or agree for that. Conceptually quite easy. It's something they could all code from scratch, like I did there pretty much in a few lines of code. It does not make any distributional assumptions on the data or the distribution point estimate. We just we need finite moments, but we don't really need to. It works, skewed distributions, heavy tail distributions, and so on. It just takes, it might not work as well, but it does work. And we have no need to collect more data. This is the kind of, obviously if we can get more data, great. But if it's expensive, if it's delayed, the event already happened, we have a way around it. Okay? But there are disadvantages. The sample may not be representative of the uncertainty of the uncertainty. So it's, when I drew different samples, I got different uncertainty. Yes, quite variant. That issue became bigger with smaller sample sizes. Any statistical method is sensitive. Sample sizes, the bootstrap is not exact. But in red, I'm going to highlight the data might not be independent, e.g. a time series or a spatial data set. and you raised a question, what do I mean by independence? Do I mean that in the observations or in the physical process? Well, it depends what assumptions you're making. But if you're assuming whatever it is that you're resampling is independent, but it's not, then you're going to run into problems with this technique as stands. And all of the above there can give misleading uncertainty estimates. But what I want to do is use this red bullet point to motivate part 2, which is to go into time series with a focus on spectral analysis. I am going to ask about that, so hopefully we can start answering that question together in this part. So I'm not going to do a complete course in time series. It will take me 10 minutes. So instead I'll do it through the lens of spectral analysis, which is a branch of time series analysis, as well as other areas of science. So we're oceanographers. So for oceanography being fine mathematicians, then we would think probably our default model of a time series wouldn't be a straight line or white noise, but actually be a cycle. Many diurnal cycles of steel sequence. It's a very nice building block. Let's just consider our time series as a basic sinusoid with an amplitude, a phase, and a frequency. We can represent more complicated functions like the one on the right as a sum of sine across with different amplitudes and phases for each component. It's a discrete sum of 3 sinusoids, and we get something that's on the left. Okay, and what is a power spectrum? Well, in its simplest form, it can be interpreted as the square modulus of those amplitudes, right? So we had 3 sine curves before with different A's. We can get the phase information that's lost in the power spectrum, and we just take our amplitudes of different frequencies, get the square modulus, and we plot those 3 values. So this is the power spectrum discrete frequency. Okay, so that's a nice interpretation of what a power spectrum is for those of you who haven't seen it. Now we could keep going and add more and more sine curves. But what if our time series processes at all frequency? And it's in some sense, by that I mean the amplitudes and the phases may be drawn from some distribution. Take the probabilistic view on that power spectrum. Well, that is to do with vector. Right? Now, what you want me to do, I am going to give you a little bit of maths, just some notation. See, it's not too much. So we're going to have a continuous real value stationary process. By that, I mean the statistical properties of the time series don't change too much in time, or a discrete one, x plus good. Angular frequency is omega in radians, or 2 pi f, f exponentially in hertz. Use omega or f, note that some are using omega, some use f. Power is a time lag, so that's measured in seconds, and I, not J, like engineers, sometimes engineers use J, is very time swap. Okay? And just to keep things simple in this talk, we're going to assume x is 0 mean. So not 0.5 like before, but just 0 mean. Xt or discrete organisms. Right, so that's just a notation. And now, this is the formal definition of power spectrum density. Spectral analysis. So we start with the Fourier transform at the top. That is just an equation you've all seen before. Fourier transform of our continuous time series x. Okay, so that's continuous Fourier transform. Or we can invert it back. So there's a coupling between the Fourier transform of a time series and the original time series. So we can interchange back and forth using Fourier transforms and inverse Fourier transforms. Now, what is the power spectral density using the notion of the Fourier transform? Where does the word power come from? Well, I like this definition. There are different definitions, and I've taken this definition, someone asked yesterday for references, so there's a book, I recommend this for anyone doing spectral analysis in time series by Percival and Ward, called Spectral Analysis for Time Series. This is on page 65, this definition. These slides will be made available to you later. So power spectral density, we can think of, well, where does the power come from? Well, let's start in the middle of this equation and work outwards. So we have a Fourier transform, right? And then we're going to integrate it. Our integral is going to be from minus t to t. Okay, so taking a longer and longer time horizon, taking the limit as t goes to infinity, and we are taking the absolute value and squaring. Now that's a measure of energy, right? So integrating over time, how much variance or energy there is, how variance there is next to t multiplied by time. But then we divide by that width of that integral, 1 over 2t, we get the power, right? So we get this in the right units, units of power of energy. So I like this definition just to understand where the word power comes from. For those of you who aren't sure, that it's a way of averaging over a window, over the width of a window, how much variability there is in the signal. One way of interpreting power spectral density is the decomposition of the variance space at different frequencies. Okay, so if we integrate back over omega, we just get the variance of our time series back. So how variable is our time series at different frequencies? For those of you who've done a time series course, you will know that this is a familiar relationship with something called the autocovariance sequence, which is the expectation of x with itself at some lag, and their derivatives. Okay, if you've not done a course of time series, don't worry about it. Right? It's a benefit definition of the power spectrum. It's a bit of that. If you don't understand that, don't worry, because what we're saying in theory is this, but we want to estimate it. And just like anything that we estimate, there will be uncertainty. So in practice, we don't observe, rarely observe a continuous signal forever. We just observe a sample, often at some regular intervals. This could be measuring the temperature hourly or daily, n times. It's a time series this time, it's not independent samples. So we can estimate the power spectral density by this equation, which is called the periodogram. It's basically the discrete Fourier transform absolute value squared. And you can see it looks similar if you squint your eyes, but a little different. There's some normalization over the width of our summation. There's an absolute value squared, there's a Fourier transform. There's some familiarity between these two things, but they are different. And remember that they are. Do not ever call this the power spectrum, please. Okay, Shen wouldn't do that. And it's an estimate. Right? So it's for the periodogram, it's defined within a range of frequencies called the Nyquist frequency. Right? So, and here's some examples. White noise, it's called white because there's a time series. Here's my estimate, I should have estimate there. I just called it power spectral density, so I shouldn't have. An estimate of the power spectral density, it's got a flat line, but it's very noisy. That's why it's called white noise. Autoregressive process, this is where we have this positive correlation in our time series, for example. That gives us a power spectral density which has more power at low frequencies and less power at high frequencies, which is why I've shaded it in red. These are often called the red stochastic processes with the analogy to the electromagnetic wave spectrum. Right? So the color red has lower wave numbers. Right? Yes. Okay, so we have a red process. We can also have blue processes, which live at higher frequencies. And they're blue. So the bottom blue on blue here, but I like that. So this is a moving average process. Both moving average processes and autoregressive processes can be red or blue. This is for magnification, but I've just shown you. And these are very kind of rough time series, very high frequencies. Right, elevated high frequencies. This one's a bit smoother, a bit more meandering, maybe like a wave. Not quite, it's not oscillating, but at least it's kind of more meandering, dominant at the low frequencies. Okay, so use your power spectral densities. Here's some power spectral densities from drifter data. Shen is our resident expert on drifters. And you can see when we plot power spectral densities with the velocities obtained from drifters, so these are velocity time series eastward and northward, we can combine them as a complex Hardy time series. And then our spectrum looks at positive and negative frequencies, this is one direction of spin, and you can see peaks, low frequencies, some peaks, but probably know this frequency, etc. So you can see these beautiful things from spectrum. I skip the next few slides because I want to talk about uncertainty. The sampling creates uncertainty, right? So in theory, we have this, in practice we have this, and repeating the earlier slide. What are the differences between the two? In the interest of time, I've skipped them to you. we're replacing an integral with the sum, right? And we are truncating, but not taking a limit anymore with a finite sample. So there are gaps between the x's, and there's stuff happening outside the values. There's two sources of uncertainty: what's happening between the values and what's happening outside the values. And for that reason, we don't know exactly what the Taylor spectrum is. So there's two sources of uncertainty. How can we reduce those and quantify them? I'm just going to give you some techniques because, skip a few slides ahead, here's an example of where we have uncertainty, because the theory says that Taylor spectrum should be the green line, but the periodogram gives us the white lines, the discrete Fourier transform. And that actually looks almost like a bias. So there's some kind of bias. And there's a quote from Tukey that says more lives have been lost looking at the periodogram than by any other action rules. Tukey had a tendency to be dramatic. As many of you might know, he worked at Bell Labs, and the Nobel Prize wins there, and although he wasn't, he developed much of the foundations of signal processing, including the FFT algorithm, but we shouldn't argue with him. So what the Tukey and others at Bell Labs tell us we have to do in our signals? Well, remember, sampling creates uncertainty. So one thing we can do, Percival and Warden on page 354, is something called modulate. Okay? For those of you who haven't heard of that, it's a clever technique for removing some what's called broadband bias and some variability in our spectrum at the expense of some narrowband bias. So we lose a bit of resolution, we sort of do a bit of smoothing in effect, which creates a different sort of bias, but we can improve that. And also at the top you see 95% confidence bands that are provided. So this is a MATLAB's multi-tapering package. Python and R also have multi-tapering packages which give you confidence bands, so you can look those up. But if you want the theoretical derivations on page 354, first of all, and this is now, I promise, I'm going to write a note somewhere. This is one area I've been guilty of. If I'm a statistician, I should always report uncertainty. I don't always do it with spectrum. I think we can get a bit lazy and just skip the spectrum, but we should actually report uncertainty with spectrum as well. And I promise to now do it. I want to say do as I preach, and I encourage you all to also include uncertainties in your spectrum. So that can account for this accounts for the uncertainty caused by the truncation, right? So before we had an integral going nicely to infinity, but now, and this accounts for the issues we had with everything outside. But we still have this issue of what happens in between observations. And here, for example, there's a Matt-turn process, but Nicole, will you cover that tomorrow a bit more? Yeah. So I won't tell you what the Matt-turn is, but even if I account and use some tapering, I still see some differences between theory and practice. There's still some uncertainty. Does anyone know what the source of uncertainty left is? Any guesses? So it's basically what I showed you before. It's we don't know what's happening between the observations. We are summing rather than integrating. And so what's wrong this time? Well, sampling isn't usually continuous. We often observe this. And all of us would probably plot this line, right? We have a time series sample, probably think it's about continuous process. And now if we restrict ourselves to the family of sine curves, actually, it could have been this sine curve that fit these points, right? Goes through the points exactly, just like the first sine curve. I could keep going, make that sine curve higher frequency. This one goes through all the points, this one goes through all the points. So does this one, I can go the other way, down, not up, starting at 0. All of these go through the points. So in 2D, this problem is known as aliasing, because in image processing as well, the aliasing problem is also known as the wagon wheel effect. We get to the cartoon. So there's a constant frame rate that's filming these tires as they spin around, right? And your eyes are often seeing it go forwards or backwards because you're just seeing between those Nyquist rates, right? You're not seeing what's happening between the frame rates. right? And for that reason, what we observe, this car's driving forwards, sometimes the wheel is going backwards, forwards, and so on. It'll move across our spectrum, even though it's going at a way higher frequency. Right? You can see this in engine propellers and other things like that too. Right? So this is a sort of uncertainty that we can't really fix. I'll take a question in a second. So we can't really fix this issue because unless we sample more frequently, we don't know which of the options it is for how fast it's going. It could be any of those signposts that fit through those observations. So if I go back to my slides, basically, if we have a model, we can try to account for it. So if we alias our return, in this case, the green dashed line now goes through the red observations a bit better. But in practice, unless we have a model to tell us how things are linked as we go onwards to infinity in this direction, what this green line basically we extend out and then we fold it back in to get this green dash line. Unless we have that, then generally you're a bit stuck. It's a source of uncertainty that whenever you think that you observe a certain oscillation, it could be an aliased version. And some instruments have anti-aliasing filters and so on. But in general, unless they've said they have one, don't assume that they do. That's an additional source of uncertainty that you should make sure that there aren't any aliasing effects, a high frequency effect that you haven't observed. Let's say you're observing, time series every 3 days, and there's a diurnal cycle. You're going to observe it in a weird way. It's going to be there somewhere, so that's not there in data. I didn't have a non-stationary time series. What people typically do in non-stationary time series is they apply some kind of time frequency spectrographs, time on the x-axis, and frequency in the y-axis, time, frequency, and a color pattern. Okay, so we have time, frequency, power, and color, and so what we see is the power at different frequencies evolves over time. Okay, so this is from a drifter, this is an inertial oscillation changing in frequency over time as the drifter moves. And the back is when it's low frequency and turbulence, that also changes. Okay. Now there's an additional source of uncertainty, and it's called the Heisenberg-Gabor uncertainty. So it's built on the principles and physics of Heisenberg uncertainty. And this is the idea that from one signal, you can't sharply localize in time and in frequency. There's a trade-off, right? So if we want to increase resolution here, we lose resolution. Or vice versa. If we want to time changes more rapidly, so we shrink this resolution, this is going to broaden, and we might lose some features of the feed as we have less data to resolve the frequencies because we have shorter windows. We make the windows longer, we can't have changes as fast. So there's this trade-off that comes here, and I just wanted you guys to know about another uncertainty we can use school. Okay, and just to give it to hear Borman say it, one is not simply sharply localized signal. That's the famous thing. So, bonus section was how to bootstrap time series. I will run over by 2 minutes because I'm just going to throw some ideas at you. One basic idea is before we showed with correlated data the bootstrap fails. We can fix that sometimes with a block bootstrap. So we basically take blocks of our time series, put them in a hat, resample with replacement. For example, this one allows. There's different ways to do it. And you can create bootstrap time series. Doesn't always work, but it can work quite nicely. Some other approaches include doing some parametric model fitting, and then either using atom properties of its uncertainties. So this is a little bit like your question earlier about if you have a model with uncertainties, model, or you can sample from the model if it's stochastic. You can use spectral analysis methods to resample as well, which in essence sample the spectrum and then take a Fourier transform. Some of you may have seen these. So there's all sorts of techniques. If any of you are interested in existing Python code this time, but not mine, but the block bootstrap, full credit to Kevin Shepherd. I think the package for doing the block bootstrap. I just coded it myself. I just wanted to show you. You remember how we had this issue here, right, that I showed earlier. where if we have correlated data, our uncertainty estimates are too low. I'm just going to run your bootstrap and say this is not an impossible challenge. I just ran a block bootstrap. Let's just run it. It'll take a little longer to run, but it's still pretty fast. And we can see that we can improve it. So before we were here, and then now we're here. So we've inflated those uncertainty estimates to close towards, it's not perfect, but it has improved our uncertainty estimates with the block bridge. So this is quick and dirty. You might find even better ways. But just so you know, there are techniques. There are techniques for inflating your uncertainty with correlated data. Some of those were captured in that last slide, the time series. There are ways in spatial statistics too, which Mikhail might cover. There are lots of different ways to make sure you accurately capture it, so we can build on basic bootstrap and still get these uncertainty estimates with correlated. And sorry for going over 5 minutes, we'll wrap up there.